Good afternoon. Today we're going to talk about light electromagnetic waves. We will discuss reflection, refraction for today, and some other characteristics of light waves. Just as other waves, light behaves just like sound, just like sea waves or other types of waves. You need to know that light waves, they are transverse waves in 3 directions. Okay. We will discuss the law of reflection. We will discuss refraction and Snell's law. And in the next slides, we will talk about the critical angle, etc. Okay. Reflection of light. What is the law of reflection of light? Now, the law of reflection of light is that the angle of incidence is always equal to the angle of reflection. Yeah, when we have a mirror, we have a normal, then need to know that the incident ray is the angle between the ray and the normal, and the angle of reflection is the angle between the reflected wave or ray and the normal. I hope after, when you come back, we can check the law of reflection, and we will do a setup with a mirror. Yeah. So if you want to set up and you want to find the light ray, I will make special worksheets wherein you can find how to find the angle of reflection and how you have to draw all the lines. Okay. So again, law of reflection, angle of incidence equals to the angle of reflection. Okay, we have a plane mirror and we have an object. Now, how does it work? Light is coming, it's reflected, right? Going to the plane mirror, and then the light is reflected. And we can do this from different points and different normals. Yeah. We can make our construction lines. To make the construction line, you draw a normal line from the object to the plane mirror. You measure the distance between that ray to the plane mirror, and you measure exactly the same distance behind the mirror. Then you will see the ray, for example, the red ray is coming in as the ray that is coming from the object. You'll have to look at the dotted line, and you draw the dotted line through the mirror to the outside, and then you find your reflected ray. Yeah, we will practice this more in the class, so you will get used to how to make construction lines. Okay, so what we actually see is an image. Yeah, we call it a mirror image. Now, we call this image that is virtual. Now, what does it mean? What does the word virtual mean? Virtual means that you actually cannot project an image on the screen. Yeah, and mirrors are a typical example of this. Okay. Now, what can we say about the object and the image? First of all, they have the same size. They have the same distance behind the mirror as the object is in the front, and the image is upright. Yeah, the same way up as the object. When we look to the back to front compared with the object, we get like a lateral inversion. Okay, and we call the image virtual. Yeah, as usual, just pause the video and make some notes so that you can continue. Yeah, it's a very simple law. I will give you, when you are back, I will give you some worksheets with some examples on how you actually have to draw the lines of construction for a reflected image and how the rays need to be drawn. Okay. Virtual images. Virtual images are formed where light rays only appear to come from. That means a virtual image cannot be cast onto a screen. Other images that we really can cast on the screen, we call them as real. Okay. Okay, let's fill in. The law of reflection states that the angle of reflection is always equal to the angle of incidence. Both angles are measured relatively to the normal, a line that is 90 degrees to the reflecting surface at the point of reflection. A plane mirror forms a virtual image which is unlike a real image that it cannot cast on a screen. The image in a plane mirror is also the same size and the same way up as the object. Now we will discuss the refraction of light. If you put a tablespoon or a straw in a glass of water, you will see it's like a strange image that you see. It's like it changes directly when you look in the water. So when you look at the water from the air to the water, you see in this case this spoon like having a different angle. On the right picture, and that's what we're also going to do in the lab, we are going to check how light is going to be reflected. Now, when we look at the red beam, the light is coming from the air and is going inside the glass. And if you look good at the beam that is going out, that is exactly parallel to the light that is coming in. When is refraction occurring? We may say when light or a wave enters a different medium or a different region, it changes the speed. The denser the medium, the lower the speed. So the speed changes usually by the way it changes the direction. So we will see a clear bending. When there is a bending inwards, you will see actually that the speed of the light decreases, and when the light goes out of the glass, it bends out, and then again the light speed increases. Okay. Now let's look at the water wave, and let's see what we all see. Okay. On the upper picture you see water waves, and there is like a triangle border. Okay. Now we see clearly that behind the border the water waves are going to bend. We also see that the distance between the lines, or the wave fronts, are smaller. Okay. Now this occurs when the water is slowing down. So the water waves slow down as they pass over from a deeper region to a shallower region. Now, if you would go from a shallow region to a deeper region, you would actually see the opposite effect. It is important to note that in IGCSE you get a question like this, and you need to know where's the deeper region and the shallower region, and you have to draw the lines, and you have to also to show that the wavelength is decreasing when water waves from deeper go to a shallow water. Okay, and it's exactly the same when light is coming down. The light slows down as it passes from air into glass or perspex or water. Perspex is a kind of plastic. The refraction experiment, which we will do in the class. You have like a ray box and a glass block. What you have to do is you have to put the ray blocks onto the glass block, and at that point you draw a dot, and from that dot you draw a normal like inside the glass and outside the normal. Now, you follow the ray, yeah, and then you can find actually the ray of incidence and the ray of refraction. So the ray of incidence is between the ray and the normal, and the ray of refraction is between the normal and the refracted ray. Again, look good at the picture and you will see that the line that is coming out is parallel to the line that is coming inside the ray, inside the glass block. Okay, so you could do your measurements and you're going to use different angles, and you need to measure the angle of incidence. Yeah. Now, when the angle of incidence is 0, that means it's parallel to the normal, it goes straight through. So the angle of refraction is 0. Okay. This is just an example from an experiment, and we see in all cases that the angle of incidence is bigger than the angle of refraction. So it is important for this experiment that you measure very good the angle, and you're going to use a protractor. Okay. We won't discuss too much the deviation, but we will use a formula in order to find the refractive index of the material. What happens? The increasing of the angle of incidence increases the deviation. Okay, and you will also see that the angle of refraction increases with an increase of the angle of incidence. Okay, let's look at this experiment again. Less to more optical dense transitions. So what do we mean by that? Air is has a much lower density than glass. Okay, so we expect that the speed of the light in glass, because of the much denser material, will slow down, therefore the light will bend. Yeah, and look again how you have to construct the angle of incidence, how you find the angle of incidence between the light of the ray of incidence and the normal. Then the ray is coming out, and again you measure the angle by the angle between the refracted ray and the normal. And we see that light bends to the normal. Okay, this is important note. When light bends towards the normal, you know that the speed is going to decrease, and that the angle of refraction is lower than the angle of incidence. So we may say that the angle of refraction is less than the angle of incidence. Now let's see what is happening when we go from a more or less optical dense transition, for example, from water to air or from glass to air. Okay, on the left side, we have the water. We have the angle of incidence. What would you expect for the angle of refraction in air? Well, we know that the speed in air of the light is higher than in water, so we expect the opposite effect. So the light beam is going to bend away from the normal. Yeah, so in this case the angle of refraction is greater than the angle of incidence. Well, maybe you might have noticed when you are going to swim and you look like from the side of the pool, and it seems like that the pool seems more shallow than it actually is. Now let's look how that is. Okay, so we have an object at the bottom of a pool. We have water and air. These are the two different media. Then light that is coming from the object. What is going to happen with the light is going to bend out. Yeah, so both are going to bend out. Now it's interesting to know when you look at this picture, and we are outside the pool, so we are standing on the side of the pool, and where the light beams are going to, or the rays are going to, there's our eye. So what do we actually see? Where do you think we see with our eyes the object at the bottom of the pool? Exactly, that's where we will see it. So we will see an image that is actually much shallower than the actual object is. This is a clear example. You need to know this for the IGCSE, and you need to know how to construct the image and understand what is happening, and you have to explain why the image, or the object as we could say, appears to be closer. Yeah, so now you understand, when you look into a pool, you look and when you see the bottom, it's much shallower. You see it much shallower, but it's actually much deeper. Now let's look at these examples, because these are examples of refraction. Okay, yeah, we have different shapes, different blocks, and let's see what is going to happen. Well, in A we know already how the light is going to bend. Let's see what is happening in the cone. It's also going to bend, but it's taking a different path. Let's look at the triangle. It's going to bend and then bend downwards. You might have seen a picture of white light, yeah? And the prism is actually used to define all the colors of white light, okay? And you might remember from your year 8 or 7 class how we call when you put white light through a prism and you will see the colors of the rainbow. We call that dispersion. Don't forget that name. Okay. In D, E, and F we have like a lens. Yeah. And let's see what's going to happen with the light. Indeed, the light is going to bend, yeah, towards the middle. Okay. We will also discuss lenses, and we also will make constructions of different types of lenses. Okay. But understand that these are all examples of refraction. So when you're looking through your glasses, or when you look through binoculars, or when you look through a lens, refraction is actually happening. Now, for the refraction we have an equation, and that is an equation that you have to memorize. Okay. When light ray passes from one medium to another, the refractive index n equals to the sine of the incident ray divided by the sine of the refracted ray. And n is a constant, and the n depends on the type of material. So again, n equals sine I over sine r. I is the angle of incidence, r is the angle of refraction, n is the refractive index depending on the material. You might have wondered why diamonds do like flicker so much. No, that is because diamonds have a very high refractive index. That means the light is bending quite a lot, much more than in other material. That's why we see a lot of flickering through a diamond. Okay, so again, remember we did this at the beginning of this slideshow, yeah? How do we find the refractive index? Yeah, you make a setup as I said before, yeah? You draw the normal, yeah, you have the ray box and the normal from the paper inside the glass block, and you're going to measure at different angles of eye what will be the angle of refraction, okay? You could start, for example, with 30 degrees, you trace the path, and you trace the path of the light ray, and you can follow and you can measure with a protractor what is I and R, okay? And from that, you can calculate the refractive index, yeah? Sine I over sine R, yeah? You have to repeat this, and you can repeat this between angles of 10 and 80 degrees, and you will see every time if your measurements are correct, yeah, the refractive index will be the same. So at the end you could calculate average value of n. Obviously, if you have a calculated n that is way off, you should repeat the angle that you measured with. Okay. Question number 1. Calculate the refractive index when light passes from air to glass in the angle of incidence is 30 degrees and the angle of refraction is 90. Pause the video and answer the question. Well, we know the formula n sine I over sine R. We fill in sine 30 degrees over sine 90 degrees is 0.5 divided by 0.326, and we will find the refractive index of 1.53. Question 2. Calculate the angle of refraction when light passes from air to perspex if the angle of incidence is 50 degrees and the refractive index is 1.5. Formula: n sine I over sine R. Fill in 1.5 equals sine 50 degrees over sine R. Then sine R equals sine 50 degrees divided by 1.5. And you will find that sine R is 0.511. And you will find an angle of refraction of 30.7 degrees. Another question. Calculate the angle of incidence now when light passes from air to water if the angle of refraction is 20 degrees and the refractive index is n is 1.33. Pause the video. Same formula. We fill in 1.33 is sine I divided by sine 20 degrees. So sine I becomes 1.33 times sine 20 degrees is 0.455, and you find an angle of incidence 27.1. Now, it's very logic. If you would get an angle that is lower, you know you made a miscalculation or something went wrong. Remember, when we go from air to water, the angle of incidence is always bigger than the angle of refraction. Copy the table and complete it and make your calculations, okay? Okay, here are the answers. For the first one, R is 35.2 degrees. R is 48.6 in the second one. I is 59.8. R is 18.6. And the refractive index is 1.53. Noteworthy, look good again at the table. what we will see is when medium 1 is less dense than medium 2, n is always bigger than 1. When medium 1 is more dense than medium 2, and you will see that from glass to air, then we will get a refractive index of 0.67, which is lower than 1. Okay? Dispersion. I mentioned it already, but it's good to repeat this again. When you hit white light on a prism and you need to know all the colors in their order, yeah, what you will see is white light in the prism is going to bend, and you will get an order like red, orange, yellow, green, blue, and then going to violet. Okay. Now, why is this happening? Actually, white light consists of all colors, okay, with a different frequency. And when light has a different frequency, it will bend in a different way. So, when we look at the prism, we clearly see that the blue light blends way more than the red light, okay? And we can see that violet has the greatest refractive index because it deviates the most, and red has the lowest and deviates the least. You have to explain this on your exam if they ask you a question about it, and explain what is happening. Okay? Understand what we mean by the word dispersion, yeah, and understand that red light refracts less than violet light. Also need to know the order of the colors of the light. So white light going in and is going to bend, and we get a nice spectrum of white light. Yeah? So from this experiment we also can conclude that white light consists of all color. Make a note of this and we continue. And to finish this episode, let's fill in the gaps. Refraction occurs when a wave changes speed as it crosses the boundary between two regions. The direction of the wave also usually changes. Light rays deviate towards the normal when they pass from a less dense air to a more dense perspex. The greater the angle of incidence, the greater the angle of refraction, so the greater the deviation. Different colors of light deviate by different amounts. Violet deviates the most. A prism can be used to split the colors of white light into a spectrum. We call this dispersion.